Okay, hopefully students did receive my emails and announcements. So there are some delays. I had a lot of things to work through. The allotted time for the quiz was, well, not estimated time for the quiz is about 10 to 12 minutes. But since this is the first one, I decided to give 20 minutes. And as you all saw with the questions, kind of like a softball, a softball approach with, with low stakes, in the sense it was very similar to the example problem. So hopefully students didn't have any issues with the system or the questions. And going forward, hopefully, everyone is now familiar with the system setup. So one thing I'd like to clarify is when I say online, I mean students are not in person. Okay, so when I always refer to online students or students who are taking online quizzes, what I'm referring it to is as students who are not in person in the classroom. Okay, the quizzes itself, of course, is on Pearson, which itself is on the web. So there could be some confusion regarding that. So all students, whether they are physically present in the classroom or whether they are on Zoom, are giving the quiz on Pearson, which would be online. But when I state online students, I mean those students who are not physically present in the classroom. And there was a couple of emails regarding that. So I will post an announcement and clarify it in an email. Okay. But for now, let's move ahead with our topic under discussion, and that is diode circuits. Diode circuits. So the first one we are looking at is rectifiers. Now, rectifiers are, that's the technical name for the circuit, but they are ever present and ubiquitous around us in all spaces. Okay. Basically, rectifiers are so called because they rectify the AC voltage to DC. So it's an AC to DC converter, which, when I use the term ubiquitous, that's exactly what it means, because it is there in every electronic device that we use. Anytime you use a wall charger, anytime you plug in a device into the wall, there is a power supply in there, in the adapter or inside the device, that converts the wall outlet, the AC voltage coming from the wall outlet, into a usable DC voltage. If you use the computer, monitor, television, projector, we take a power cable and you plug it into the wall, there is a rectifier circuit inside each one of these devices. The desktops that you see, there's a big power supply in the back of a desktop. Okay. If you use a laptop, you have this charger. Charger is an example of a rectifier circuit. If you have access to an old one that no longer works, you might want to open it up and you can take a look at the components inside. Pretty much what you'll see is a rectifier circuit made up of diodes, and then there will be filters and regulators. Okay, so we're going to see how we can use a diode for rectification. So there are two kinds of rectifier circuits that we can create with diodes: half wave and full wave. A half and full. And both of these refer to the positive and negative half of a AC voltage. So AC voltage has multiple cycles in 1 second. Each cycle has one half cycle, one positive and one negative. So a half wave rectifier would convert only half of the AC cycle. A full wave rectifier would convert both cycles, positive and negative. Half wave rectifier would be either positive or negative, depending on which way you connect the diode. Okay. So the simplest circuit is simply a diode that you connect to an AC source. That's it. That's the simplest. So the circuit comprises of just one single diode. That's it. Nothing else. So if I was to break this circuit up as a real life example, I could state, let me change the color. This would be my AC source, perhaps a wall outlet. And this would be the load. And the load RL could be anything, any device. So again, there's not much to a circuit. You simply have a diode, you connect it to a source, and it's a half-wave rectifier. So now let's see how it would work as a half-wave rectifier. In the circuit here, we see, let me clear this out. You see there's a diode that is connected to the positive end of a supply. Okay, AC signal is shown right here. There is a positive half cycle. And this is the negative half cycle. So what happens? In the positive half cycle, the voltage is climbing in the positive direction, meaning, excuse me, meaning the diode's anode, which is on the left, is now higher than the cathode. So the diode is on in the positive half cycle. Okay, it's on in the positive half cycle, and it conducts, it allows passage of electrons. So in the positive half cycle, you have current flowing through that load resistor. Negative half cycle, the exact opposite happens. The diode is off. So let's see. Better. Diode is off because the AC voltage flips. It's now going in the negative direction. So the anode of the diode is lower than the cathode. Okay, anode of the diode is lower than the cathode. So that means it is reverse bias. Here it is forward bias. Here it is reverse bias. So it's off. And so across the load resistor, the voltage, if you monitor it, looks like this. So V out of T is voltage measured across RL. And both halves are now positive. So at this point, let's take a pause. You think over that operation and let me know if you have any questions. Any questions at all? Yes. Yes, it does. So there are current waveforms also. So when it's forward bias, the current will follow the pathway of the diode current. Yes, that's what would happen. This right now is simply showing you the voltage as a function of time. So it is not current or voltage, it's simply the voltage across that load resistor, V out of T, VO of T, as a function of time. So for now, we're only interested in the voltage. Current would just take, we won't investigate that in 321. But does this make sense? This is the basic operation or operating principle of a diode circuit, right? We learned about the ideal diode. Ideal diode is either on or off, and we extend that principle into creating a circuit that can take an AC voltage, positive, negative half cycles, and convert it into a unidirectional circuit. I mean, unidirectional waveform. So voltage is now going in the positive direction. Yes. Yes. Actually, the question being asked is when it's off, the cathode is higher. The answer is yes, but I would quantify that by explaining that the cathode is higher than the anode. That's why it is off. Make sense, right? So you have an anode and a cathode of the diode. If the anode is higher, the diode is forward bias. If the anode is lower, then it's reverse bias. That's all. One-way valve. One-way valve. Any other questions? So right now, the first question that would come to my mind is this DC? Can we consider it as DC? The answer is it is actually both, right? The voltage is varying, so it is AC, right? It's not pure DC. It's not pure DC. The waveform is fluctuating. Anytime a value of a waveform changes with respect to time continuously, we say it's an AC waveform. So how can we call this as DC? It's kind of ambiguous. You can call it AC, and you can also call it as DC. Then there are other components that we add to it to make the shape as flat as possible, okay? But the way we would use this as DC is we would use the average value of this waveform, or average value of the voltage. And we could say that the average value of this waveform or voltage would be a summation of 1/2 cycle, right? Area under the curve. We saw it was 0.637, but because it's only half, meaning here it's 0, here it would be half of 0.637, and so the average value of the voltage would be 0.318 times the peak value of the AC waveform. So if the AC waveform had a peak value of Vm, which is right here, and 0.3 would be somewhere here. Okay. And again, I always like to use the analogy that consider it as a mountain of dirt. If you completely flatten out that mountain, that's the average value of that waveform. All right, let's take a pause. Let me know if you have any questions.
I got a quick question.
Yes, go ahead.
Why do we do 0.318 instead of 0.637?
Because the second half cycle is 0. So the value of this is 0. If it was just 1/2 cycle and we would simply take, just average out 1/2 cycle, we would say it is 0.637. But if we integrate from here to here, let me show you this. So from here to here, the first time period, this would be 0.637 times Vm. But because we are considering one full cycle of the AC voltage, we have to take the DC corresponding to that one time period. So then this becomes 0.318. And that's the biggest drawback of a half-wave rectifier. Does that answer your question?
Yes.
Okay. Question? All right, well then let's move into a full wave rectifier and let's see what happens. So in a full wave rectifier, there are two kinds. This shows a what is known as a center tap full wave rectifier. And this is the most common one. It is a bridge rectifier. So this kind of circuit connection is known as a bridge connection. It's like 4 components connected in a diamond shape. This is known as a bridge rectifier. This one requires a center tap transformer. So right now, this just shows you a source, right? 2 sources, but it's basically an AC source. In real life, what we had were transformers. So transformers, not the Michael Bay ones. These are basically 2 inductive coils that are linked together. Okay, this is also the operating principle of a wireless charger. Right, you have your smartphones. On the back of your smartphone or a smartwatch is a small inductor. There's a coil that's on the back of your smartphone, and your wireless charger, which is connected to a USB source, also has a inductor. When you take your smartphone and you place it on top of your wireless charger or wireless charging mat, the 2 inductive coils link up. They both have magnetic fields. The magnetic fields link up. So the energy from your wireless charging mat is now transferred into your smartphone through the linked magnetic fields. The entire world runs on electricity, and that electricity is possible, or the distribution of that electricity is possible due to this amazing piece of technology. Okay, a transformer is so called because it transforms the value of the voltage. You have 2 inductive coils that are wound around a same core, right? So an inductor is wound around a core. If you take a magnetic core and you wind 2 coils at the same time, you have a primary coil and a secondary coil. So you have a primary inductor and a secondary inductor. They're both physically in contact. They're tightly wound around the same coil. And there's a lot of equations and derivations that take place. But in short, what you can do is, depending on the number of coils, you can either step up the voltage or you can step down the voltage. And as I said, there are a number of equations that govern this, but you can easily step up voltage or step down the voltage. And this, of course, is all for AC power generation and transmission. So the way those adapters used to work is you'd have a transformer in there, you'd plug into your wall outlet, which would be 110 or 120 volts. That 120 volts would be stepped down to about 10 or 15 volts. Then the output of the transformer would be connected to a diode. The diode would convert it into DC. We'd add a filter and a voltage regulator, and we'd have a flat DC line at the output. Till today, that is still the operating principle of a charger. Okay, anytime you take those mini chargers and you plug it into the wall outlet, the USB chargers, that is what they're doing. Okay, they have gotten more and more sophisticated. You don't have those heavy transformers anymore. By the way, has anyone ever used one of those? They were known as wall warts. Typically came inside a dark colored or a black colored plastic case, and you plug those into the wall directly. Cordless phones, perhaps, any other kind of cordless tool, like cordless screwdrivers, drills. You still have those heavy wall warts. Anyone ever seen those, used those? There's a transformer inside it. That's why it's very heavy. In modern chargers, what it does is it converts the wall outlet frequency, 120 volts, directly into DC. That high voltage is converted directly into DC. Then it is passed through an inverter circuit, converted back into an AC at high frequency transformer. And again, there are lots of equations that go on this, but because it's high frequency, the transformer size is now reduced. It's very, very small. It does not have to be large. So anyway, modern chargers that you use nowadays still use the exact same principle. And then there is a center tap transformer. So you have multiple coils, and depending the number of turns, you can have the output voltage or different output voltages. So this one is a center tap. Center tap transformer. And what it does is it splits the secondary coil into two parts, plus minus and plus minus. That's due to the design of the transformer itself. Okay. And that's what is being displayed with these two sources. So in real life, those two sources are basically just one device. It's a center tap transformer, and you connect two diodes at both ends of that transformer. And the way this would work is, it'll be easier to describe the operation like this. So I'm just going to draw the secondary coil. And you'd connect your resistor in between. So let me make this bigger. Notice that both diodes are pointing in the same direction. But here's what happens. In the positive half cycle, the transformer is plus minus, plus minus. And this is the center tap, center line. What happens to diode D1? Diode D1 is forward bias. Diode D2 is reverse bias. So in the positive half cycle, diode D1 is forward bias. This one is reverse bias. Make sense? Right? Positive half cycle is connected to D1. That means anode is higher than cathode. Here, negative is connected to the anode of D2. So D2 is off, D1 is on. And because it's on, current flows to that load resistor, entering from the right. And so you have a plus on the right, minus on the left, negative. Now, when it's reverse bias, this is minus, this is plus, this is minus, this is plus. So for a negative half cycle, minus, plus, minus, plus. And that's the center tap. So reverse bias, forward bias. Current is now flowing this direction. And yet again, it still causes a voltage drop in the same direction as plus and minus. So for a positive half cycle, diode D1 is on or diode A is on. Here I would say D1 on, D2 off. D1 off, and D2 on. The result is that for the load resistor, the current flows in the same direction for both cycles, and so both halves are rectified to DC. Both half cycles are used, are rectified in the same direction. And now when you average it out, the average value is much higher. And this would be 0.637 times Vm. Okay, 0.637 times Vn. All right, let's take a pause. Let me know if you have any questions. If you have no questions, we'll take a break for about 5 minutes. We'll resume again at 11:07. And I'm available here to answer questions.